our next speaker is Elsa Teixeira, and she's going to speak about an interacting dark sector from fluid approximations.
Thank you to the organizers for allowing me to give this talk today. So I'm going to talk about how we get an interacting dark sector by employing fluid approximations. And this is some work I have been doing with Carsten van der Broek, Gaspar Poulot, Nelson Nunes, and Eleonora Di Valentino. I'm going to show also some nice pictures along the way that were made by my friend Inês Oliveira. If you want to check, I have put her website over there. Okay, so I'll try to not be very repetitive. So we have our standard model of cosmology, which is the lambda CDM model. And I just always like to highlight that we have a few different categories in the standard model. So we have things that are standard physics that have been well tested and are quite, whose nature we quite agree on, let's say. So we have our theory of gravity, which is GR. We have our metric ansatz, which is the FLRW metric assuming homogeneity and isotropy in the universe. And we have our standard matter that is included in the standard model of particle physics. And then we have the things on the right-hand side, which are the things we have somehow inserted in the theory to solve problems that we came across. And we have a lot of evidence for them, but we still don't have a clear consensual answer for their physical nature. So this would be our theory of inflation, which we usually assume just to be some kind of early accelerated expansion in the early universe that gave us the seeds of structure formation. Then we have dark matter, which in the lambda CDM is our cold dark matter that explains the formation of structures and the dynamics of galaxies. And then we have our lambda, which will give us or explain the dynamics in the early universe and the accelerated expansion we observe today. Okay, so this is the reason why we're here. We have heard a lot about these cosmological tensions. So we already discussed this. We have our measurements coming from the CMB. So this measurement gives us something of the order 67, 68. But in reality, we are measuring something in the early universe, as Tanvi explained very well today in the morning. So we are measuring our sound horizon, and then we are propagating this using the lambda CDM model in order to derive a value for H naught. So the CMB is also, I think we should not forget, is also a great confirmation or a great support for the lambda CDM model, and just shows how far we have come. So we see over here, the blue curve is the prediction from lambda CDM that fits the measurements really well. But we still need some kind of theoretical model in order to derive our value for H naught. Yes, so we have our distance ladder measurements that give us some local measurements, and these will not be in general dependent of the cosmological model, and they give us a consistently higher value for H naught that is model independent. Okay, so this is the same information. So I have put here a similar version of the plots we have seen with the different measurements we get from measurements from early universe physics and from late universe physics. We see that we have this tension is always around 5 sigma if we consider, for instance, the Schu's value and the CMB Planck value. And we have now a constraint coming from the DESI results, which is consistent with CMB, but again assumes a CMB value for the sound horizon so that we can derive H naught. Also, as we have seen from Adam's talk yesterday, it's also that we would need to consider a lot of systematic effects in order to explain this, in order to explain the consistency of why we have so many values here on the right-hand side, while the early universe ones are all well constrained on the left-hand side. And so it seems like one option would be to look whether there is something missing in the standard model. So we have also heard about the SA tension. So again, I'm not going to spend much time explaining this, but the idea is again that we have a bit less significant tension in the measurement of the clustering amplitude given or parameterized by this parameter S8, which is a combination of the amplitude sigma 8 and the omega matter. And I have also included here the E Rosita that we also heard about today, which gives us a prediction that is even higher than the Planck one, and also the cosmic shear one, which gives us a consistently smaller value. Okay, so when we talk about introducing new physics or changing the cosmological model, what we mean is that even if we look at the lambda CDM model and we just change some parameters or the behavior of some parameters in the lambda CDM model itself, we can already get quite different predictions to fit, for instance, the CMB data. So here I have plotted, for instance, if we make a few variations, either in, let's say, omega baryons, H nodes, or NS, for instance, for inflation, and we see that this can drastically change the fit, for instance, to the CMB power spectrum. And so the idea is that we change, for instance, the CMB power spectrum, but we also change the matter power spectrum, so we can also somehow address the S8 problem, for instance. Okay, so then if we want to go beyond the standard model, what I would assume that makes sense to look at first would be to look at the right-hand side of this plot that I showed in the beginning, because these will be things that, again, we are not completely certain on the physical nature. So I'm going to show some kind of extensions we can make both on the dark matter and on the dark energy side. So first, if we look at the dark energy side, so in the lambda CDM model, we have our cosmological constant. One way to extend and go beyond this formalism is to consider that instead of having a cosmological constant, we have a scalar field. The advantage of having a scalar field is that it's no longer a vacuum energy that stays constant with the expansion, but instead we have a scalar field that is dynamical and that can evolve with space and time, and then probably could better fit to the observations. Now, another thing that we can consider is whether the dynamics of this scalar field can affect the dynamics of the other components in the universe, so if there can be some sort of interactions. And these interactions could also give us some kind of new physics that we would not expect to observe. This is also in line with what we have been hearing recently, so the measurements of BAO coming from DESI, which when combined with supernova and CMB results seem to indicate some slight evidence for dynamical dark energy. Okay, then if we look at the dark matter side, I think I always like to highlight the fact that dark matter seems this mysterious thing, but it's actually something that is not just needed to explain one thing, is it needed to explain the whole history of the universe, since the universe was 1 second old, basically. So it's important to explain what happens in each of these epochs that I have highlighted here. So we needed to explain the formation of cosmic structure, we needed to explain galaxy clustering, we needed to explain supernova, so we needed to explain even the formation of matter. Still, we don't have an agreed upon candidate for dark matter, so I guess the most popular candidate would be the weakly interactive massive particles, but we have still not directly detected them. So I have sketched over here, I'm not sure if it's very visible, but this is just to give an idea that when we look for dark matter, we have candidates whose mass can range from something like 10 to the minus 10, 20 EV, to something like 10 to the 30 EV. So we can have things spanning a whole range of masses, and they will have different properties depending on their mass. Yes, so we have, for instance, when we go to the scales that are quite small, so below the EV scale, we'll have matter that can be bosonic. It will usually be non-thermal because we don't want it to interact electromagnetically, but we can describe it by a classical scalar field. I added also here something similar to what we heard yesterday about the stochastic background of gravitational waves, but just to say that ultralight dark matter has also been suggested as one of the imprints for the stochastic background of gravitational waves. Okay, so then this is one type of model I would like to talk about, which is what if we have this dark matter that has some kind of ultralight dark matter behavior or an axion-like dark matter behavior, and also has a time-varying equation of state that comes from the fact that it's interacting with this dark energy. But so I will explain. So when we have an ultralight dark matter, this means that we have usually something that is parametrized by a scalar field, and this scalar field is oscillating very rapidly in a potential. So we have a potential that can look something like this, and we have the scalar field being very well balanced on the top of this potential. And then at some point we have a phase transition, and the scalar field decays to this minimum over here and stays oscillating in this minimum. And this is what we see in the plots over there. So we see here that the field, this is the evolution of the dark matter field, so the axion field is very carefully balanced here, and then we have this phase transition and the field starts oscillating over here. So then we can propose an ansatz for the way this scalar field is oscillating, and this is what we have over here. And then by using this ansatz, we can apply the dark matter properties and make some fluid approximations to somehow get rid of these oscillations or approximate these oscillations into an effective behavior. We can do this if we assume that these oscillations are happening at a rate that is much faster when compared with the Hubble flow. And so on cosmological scales, we can approximate these oscillations, and this is what you see over here. So while the blue is the exact solution that is oscillating for the raw dark matter over here, if we do the approximation, we capture the similar behavior, but we don't have the oscillations. Yes. So then what we can do is we have to take all the scalar field properties of this scalar field and make some kind of approximations, which is we have to make these time averages, assuming again that the field is oscillating on scales that are much smaller than the Hubble flow. This is the same as saying that the field will be oscillating if its mass is greater than the Hubble rate. And so we can average these oscillations, and when we do so, we can still recover the pressureless behavior of dark matter. So this is what we see here. We recover the pressureless behavior, so dark matter is still decaying as a to the minus 3. Okay, but the idea is always this. So we take the scalar field properties and we rewrite them as fluid properties. So the fluid properties would be rho, p, and the equation of state at the background. So this has been shown that when we do this, when we take axion like dark matter, what we can achieve is a suppression of the matter power spectrum, particularly on the small scale regime. So we see here that we have the matter power spectrum for lambda CDM in green, which is the one on top. And then if we change the mass of this axion-like scalar field, so of this ultralight scalar field, if we change the mass, we have greater and greater suppression of the power spectrum at smaller and smaller scales. Now, you see that this suppression only happens at the small scales, and the reason is what we see here. So when we derive all the fluid approximations and we get to the perturbations, we can derive a similar approximation for the sound speed. So this would be the equivalent of the equation of state parameter in the perturbations. And we see over here that this has some dependence on the mass of the scalar field for scales that are larger than the 2 times the mass of the axion. Then this doesn't happen if these scales become smaller, and so this is why we see that here for small k large scales, we don't have this suppression. Okay, so then what we wanted to look at was what if on top of these there is also some kind of interaction with this axion scalar field and the quintessence scalar field for dark energy. And the original idea for this was taking the models that have been studied a lot by Eleonora and Alessandro and Olga that have couplings of this sort. So they have couplings that depend on the equation on the rho phi, on the rho dark energy, and on the Hubble rate as well. But these have to be imposed at the level of the field equations, and so we were trying to find some kind of Lagrangian description to derive this type of coupling, since it's known to help alleviate the Hubble tension. So what we did is we took the same kind of conformal transformations like Tanvi talked about today as well, which just means that we go into the Lagrangian and we assume that the scalar field that we have in the theory has some kind of gravitational effect on changing, for instance, the mass or the gravitational interaction of the other matter fields around it. Usually this is done using the dark energy scalar field, so assuming that the dark energy scalar field is some kind of vacuum that changes the geodesics in which matter propagates. But in this case, since we have 2 scalar fields, since the dark matter is also a scalar field, an axion-like scalar field, we inverted the roles and assumed that somehow this interaction is being mediated by the dark matter scalar field and not by the dark energy scalar field. And then when we do so, we end up with some coupling that is now dependent on this rho dark energy. So now this sounds very simple, but then in the end, when we do this with the axion field, this means that we have to propagate all these approximations to the coupling as well, not just to the fluid behavior of the dark matter. So again, going back, if we have this kind of potential, we now have 2 scalar fields. We have this interaction being mediated by the dark matter scalar field, which is this chi over here. And this just means that we have a bunch of terms that depend on dark matter in the dark energy Lagrangian. And when we derive the equations, we will have this dependence explicitly appearing in the coupling. So we see this over here. So this is the equation of motion for dark matter, which depends on this coupling over here, and this coupling depends on the dark matter fluid itself, but also on time through all the components that we have in the universe. So now we have to, if we want to write this as a fluid description and not as a scalar field, we have to perform all the fluid approximations. So we need to assume an ansatz for the oscillations of the axion scalar field. But now we have to add to this ansatz that we no longer want it to be evolving such that it will decay as a to the minus 3 when we average out the oscillations, but such that we still have some kind of behavior that is being given by the coupling if the coupling is small enough compared with the main behavior of the scalar field. So again, this just amounts to averaging out all the field quantities and turning them into fluid approximated quantities so that we can see how the fluid behaves. So I will just show you what we obtain when we do this. So in this case, because now we have this coupling, we have, when we average out the equation of states of dark matter, we see that this is no longer 0. So we no longer have a pressureless approximated fluid, but instead we have something that will be slightly positive throughout most of the cosmic history, but in the present it can take on slightly negative values. So here these values are really exaggerated, so it would never be these kind of values, it's just for illustration purposes. But the idea is that we will have some kind of negative contribution from the dark matter approximated fluid at late times. So we think that this could help address the Hubble tension because we will have an additional negative contribution, but for now this is just speculation, and this is the form of the equation of state parameter. Then we can do the same for the sound speed of the axion field or of the ultralight scalar field. And we see that when you do this, we get exactly the same terms that we had before, except that now we have these terms that depend on the coupling that we have introduced. And so when we do so, now instead of having just a suppression on the small scales of the matter power spectrum, we will have a different suppression at different scales, but the suppression will be present at all scales because of the coupling that will be turned on at all scales. This will be most effective at late times, which is when the fluid is coupled to the dark energy scalar field, and the dark energy scalar field is becoming important. And when this happens, we will see again that it's specially enhanced on the small scales, but it's enhanced on all scales, the sound speed, and therefore the matter power spectrum is suppressed, the opposite. So again, we speculate that this suppression at small scales could help with the SA tension because it could give us a smaller prediction for sigma 8, but this is still a speculation, and we are now also with Eleonora implementing this on a Boltzmann solver and trying to get predictions and constraints. So what I have shown is that we have these tensions in our lambda CDM model, and in particular, since we are getting increasing precision and we are getting probes that will give us better and better data, it's good that we have frameworks that are prepared to be tested against this data. We have been trying to look at frameworks in which we try to get some kind of physical intuition to the nature of dark matter and dark energy and see whether changing properties of one or the other that can in principle be tested also by particle physics can give us some hints on the origin of these tensions. We saw that by having scalar field dynamics, we get modifications that are not necessarily trivial in the observables. So in this case, I talked about the matter power spectrum, but this would also leave signatures, for instance, in the CMB and in the lensing spectrum as well. And we saw that in this case, we have changes in the matter power spectrum at all scales. So this could in principle be probed by different observables. Okay, so now, yes, thank you for your attention. And again, this is my friend's website if you want to check it out.
Thank you, Elsa. So we have time for questions.
Okay, thank you very much for the talk. It's a very interesting idea. I was happy if people play with the dark matter because we can do everything. We don't know Lagrangian, right? Exactly. So, but I was wondering, you know, of course, there's an old idea that some of the dark matter model could have self-interactions, and I mean it's different physics. But at some point, what I'm getting to is that you could use some of the observables, like for example, bullet clusters that have a strong constraints on the cross-section because of the fact that you cannot have too much interactions in the core, in the high density region. So something that should be also relevant for you, Kate. Did you look into that, or you have an idea how to maybe map these constraints on your theory?
No, that's very interesting, but no, we have only looked at the constraints that there exist for the mass, for instance, coming from this, but never on having just a partial contribution from the coupling. That's very interesting.
Okay, thank you.
Thank you for the nice talk. So I just wanted to ask, like, are these QCD axioms, or what kind of axioms are they?
No, they're cosmological axions, so you need to assume different mass ranges, I guess.
How are you generating the mass? Because like for QCD axioms, like at QCD phase transition, they obtain masses. Here, how do you generate masses for these axioms?
So you don't, you just assume that you have these two scalar fields, and you assume that the scalar field is there to begin with, and it has this self-interacting potential, and so then the mass is generated when there is a phase transition here. So then here the field is frozen, and then you have some kind of phase transition, and this happens when the mass is approximately of the same order as the Hubble rate. So you have this transition in which the oscillations are triggered, because then the scales in which the oscillations are happening are comparable to the Hubble rate. And so when this happens, it starts oscillating, and then its dynamics starts being important.
Yeah, because I'm asking this because like these are ghosts and bosons, right? Mm-hmm. When you break a global symmetry, these are massless bosons.
So I think you have to assume that they are massive to begin with.
So
right?
you have to add explicit mass term for
Yes.
the bosons, right? Okay, so and did you also do gravitational studies in this? Did you plan to do gravitational wave analysis for these? Because if you are breaking a global symmetry, you can have a global cosmic strings that can generate gravitational waves. So if the breaking scale is of the order of 10 to the power of 14 GeV or so, around that scale.
So I think it has to be smaller, so it has to be like 10 to the minus 20, 10 to the minus...
Not minus, plus 20, plus 14, I'm talking about gut scale, so the breaking scale. So when you talk about axion, it's axion decay constant.
So I think it's a different thing, because when you have QCD axions, you're looking at completely different scales than when you have cosmological axions, right? So you're looking at you're probing different effects, right? So it's not happening at the quantum level, right? You're not probing the same effects.
Okay, so you were talking about gravitational waves in your earlier slides. So how those gravitational waves will be generated? I mean, I did not understand.
So this is the stochastic background of gravitational waves. So this is assuming that you have the scalar field is frozen. If it's frozen right here, you'll have some kind of background that is still contributing, even if it's not evolving. And so this background can still be present and interact with the medium, I guess, and generate this. They just have to be very small because it's not contributing much to the overall dynamics.
Thank you.
Thank you.
Thank you again.
Thank you.